Okay, section 7.2, we're going to discuss finding volumes of solids of revolution. So a solid of revolution is something that you get when you rotate a particular shape around an axis. So you see some objects here: piston, a bottle, a pill, a funnel, looks like a rotor. So lots of different objects are formed by rotating a curve around an axis. And we're going to work towards finding the volume of these shapes. Now, sometimes if they're regular shapes like cylinders, we already have formulas, but a lot of times they have curved shapes for which we don't have formulas. We need the methods of calculus to try and find those shapes. So you should have a handout in front of you, or come on up and get one. The way we're going to approach this is we're going to take little slices in our region and rotate them around an axis. So here's what it's going to look like. Here's your curve. You're going to rotate this around the x-axis. And just like we did with the area, we're going to take a little slice. So that slice has a dx or delta x thickness. When that slice gets rotated around an axis, it forms a little cylinder, or not a little cylinder, a little disc. We're going to add up the volume of all such disc. Now, this is just a Riemann sum. But if we take the limit of the Riemann sum as our slice decreases in thickness, then this shape is going to merge into this shape. We're going to end up with the volume of this object being the limit of the Riemann sum, or basically an integral. So that's where we're going in this section. So my apologies to the audience at home. We don't have a nice home audience, or I don't have a way of doing this at home, but here's kind of another visual demonstration. Ooh, ah, right? So what's going to happen is you've got this shape. We're going to rotate this shape around the x-axis, and as we do, all right, I think it's time to invest in some new capital here. It's going to sweep out a volume. We're going to try and find the volume of that object. So let's start with problem number 2. Yeah, it's definitely time to rehabilitate this one. All right, so problem number 2 gives us the equation y equals 4x, or 4 minus x squared. Now, in its own way, it's drawn out in an exaggerated form here for you. What we're going to do is rotate this around the x-axis. So, like that. And as we do, we're going to pay attention to the volume traced out by one slice. So let's take a slice. Your slice has to be perpendicular to the axis of rotation if you want to do things by the disc or washer method, which is what we're doing here. So as we take that slice and rotate it around the x-axis, this, as it rotates around, is going to sweep out a little short cylinder, or a disc. Sometimes I like to call it a hockey puck, depending on how the wings are doing. So, in any case, we want to find the volume of that disc. And we're going to add up the volume of all such possible disc throughout the region. We'll start by recalling the formula for the volume of a cylinder, because basically this is a short cylinder. The volume of a cylinder is going to be the area of a circle, pi r squared, times the height. Now, what do you suppose I'm going to use for the height here? Height is going to be this dimension right here. It's going to be your dx. So that's this right here. So this disc is just turned on its side from when it gets rotated around the x-axis here. So the height is going to be dx. And now I need a way to figure out the radius. So let's just put a point on this curve, call it x and y. Then here, this would be x and 0. The radius is going to be this distance right here. That's your radius. Well, what is that distance? That distance is the difference in the y coordinates. Y minus 0. Now you don't necessarily have to put y minus 0, but I'm trying to get you into a little bit of a rhythm or habit for later on when we start dealing with things that end up being a washer, not a disk. But y minus 0 is your radius, or just y. Unfortunately, we're going to have to do this in the variable x. So I needed an expression in terms of x to replace our y, because we can't integrate pi y squared dx. We need to have this all in terms of x. So what could I put instead of y? Get 4 minus x squared, squared again, dx. Okay, so let's see what happens from next. That's the volume of one disk. We need to add up the volume of all such disks. Now that adding them up is really a sum, but as these disks get arbitrarily small in their thickness, that sum passes in the limit to a Riemann integral. So let's integrate. We're going to integrate pi times 4 minus x squared squared dx. But what are our limits? Where's our... Good. 0. 0 is the farthest to the left that we can be and still be in this region. And 2 is the farthest to the right. So 0 to 2. As far as the rest of this is concerned, I'd probably take the pi out in front, square this out. 0 to 2 of 16 minus 8x squared plus x to the 4th dx. And then just integrate from there. So it's going to be pi times, let's see, 16x minus 8/3 x squared plus x to the 5th over 5. Thank you. X cubed. Between 0 and 2. So it's going to be pi times 32 minus 32 over 3. No, 64 over 3 plus 32 over 5 minus 0. We'll just let our calculator do the heavy lifting on this one. So 32 minus 64 divided by 3 plus 32 divided by 5. And then answer the fraction. There you go. 256 over 15 times pi. 256 pi over 15. Yay. Works out pretty nicely. The big thing for you is to make sure that this slice is perpendicular to the axis of rotation, and that when you integrate, you're integrating with the same variable that represents your slice, the width of your slice. So, how are we looking on that first one? Okay? All right. Anything I can help out on? A little bit more detail here? All right, let's move on down to problem 4 then. This time we've got the function y equals the square root of 9 minus x squared. Now, realistically, this isn't drawn very carefully in terms of your handout because it should look like a quarter of a circle. It's okay. We'll ignore that part. All we really need is to try and get our bearings in this problem. So we'll take another slice perpendicular to the axis of rotation. The axis of rotation is once again the x-axis. That slice has a dx thickness. Volume is pi r squared times the height. Putting a point here has coordinates of x and y, generally speaking, and then x and 0. So as before, the radius is just the y height. But instead of writing just y, we could replace that with 9 square root of 9 minus x squared. Let's put that in here for the radius. 9 minus x squared, squared. Actually, square root of that squared. Times the height, which is dx. Does this simplify at all? Yeah. The square and the square root cancel each other out. All that's left is pi times 9 minus x squared dx. And yeah, that's going to be a nice, pretty straightforward integral. Nick, what are we going to integrate from? Good. 0 to 3 of pi times 9 minus x squared dx. Actually, straight bar. 0 to 3 of 9x minus x cubed over 3. So pi times 27 minus 9 minus 0. So 18 pi. Looks good. Let's turn our attention for a moment to kind of a more general version of this problem. Let's see if I can't give you at least a decent artist rendering of this. Are there any thoughts to wrap up on problem number 4? We're okay here? Okay. Let's look at this in a more general vein. Suppose I were to look at the top half of a circle. That is, a circle is x squared plus y squared equals r squared. So if I solve for the top half of the circle, y squared equals r squared minus x squared, or y equals the square root of r squared minus x squared. So that's the equation of the top half of the circle. The bottom half would simply be the negative root. What's the radius of our circle? What's the radius of the circle? R. Yeah, R. Thank you. So r to minus r here. Okay, looks good. What kind of a shape am I going to get if I rotate this circle around the x-axis? Sphere. So if we follow this problem through, what we're going to get is the formula for the volume of a sphere. And let's do that. Let's take our slice. So it's a dx slice. We're rotating this around the x-axis. So we have points at x and y, and then x and 0. The radius, as before, is going to equal y, which also equals the square root of r squared minus x squared. Okay. So the volume of one slice or disk is going to be pi r squared dx, which is pi times the square root of r squared minus x squared squared dx. And I guess I'm off the screen a little bit. This is going to simplify to pi times r squared minus x squared dx, like that. And we'll integrate that. Pi r squared minus x squared dx. What should my limits of integration be from? Negative r to r. Although there is something you can do here. Right. This is an even function, so, and you know, one way to detect that it's an even function is by its graph. The graph is symmetric with respect to the y-axis. So 2 pi times the integral from 0 to r of r squared minus x squared dx. Well, now we need to find the antiderivative. Here's probably a good reason why I always want you to put in the differential, because it's telling you what you're integrating with respect to. What's the antiderivative of this? Some nervous looks around. Almost. The x cubed over 3 is right. Not 0. Let's think for a second. If you were integrating, say, 1 to 3 of 7 dx, what would you get? 7x, right? It's just 7's a constant, so you could actually factor that out and say, all right, the integral of 1 is going to give me an x. So essentially this is the same thing. It's a constant. Why do you know it's a constant? Well, what are you integrating with respect to? You're integrating with respect to x. So this is effectively a constant. So what you're going to get is 2 pi times r squared x minus x cubed over 3 between 0 and r, which is going to be 2 pi times, if I plug in the r, I'm going to get r cubed minus r cubed over 3. When I plug in the 0, I'm just going to get 0. If I get common denominators here, it's going to be 2 pi times 3r cubed over 3 minus r cubed over 3. In other words, 2 pi times 2r cubed over 3. But the 2 and the 2 can multiply. What do I get when I'm all done? 4/3 pi r cubed. And that should be a familiar formula. That one should be something that you've seen for quite a while. But now, the really cool thing is that you actually proved it. The amazing thing is that Archimedes of Samos, a Greek mathematician over 2,000 years ago, also found that formula. Of course, he didn't have calculus available to him, although he did use methods that were kind of foreshadowing calculus way ahead of his time. But this formula has been around for quite some time. So, pretty impressive. How are we looking on this one? Okay? Yeah, did you like that one? Yeah. Yeah? It's kind of cool that, I mean, it's this formula you've known for so long. Yeah. Well, now we can prove it. The cool thing is if you take its derivative, remember the derivative represents the rate of change. If you take its derivative, how is a surface of a sphere changing? Well, it's changing right at the surface area. So if you differentiate this, you'll actually get the formula for the surface area of a sphere. So, nice, good stuff. Okay, let's continue with these methods by disk and by washer. We're going to move up to problem number 10. This time we have a function of x. X equals negative y squared plus 4y. hopefully you recognize that because we've got a squared term in here that you expect a parabola in shape. If you were stuck trying to graph this at home, you can't plug this into a graphing calculator. Why not? Yeah, it's x is a function of y. You need to do y as a function of x. Yes, sir. Yeah, they do. You can do it parametrically. If you wanted to set it up, you could do it parametrically. So you could let x equal, or y equal t, and then x equal negative t squared plus 4t. So you could, yeah, you could do it parametrically. Yeah, good question. Okay, so this time we're rotating around the y-axis. Now you have to take a slice perpendicular to the axis of rotation. So what kind of a slice am I going to end up taking in problem 10? Horizontal. And what's the height of my horizontal slice? dy. This is going to be a dy slice. Alright, so there's our dy slice. Taking it perpendicular to the axis of rotation. You know, a couple of the points that I'm going to give you when I grade exams is, do you take the right slice and in the right direction? If you were to take a horizontal slice when you're rotating around this axis, you're not going to get a disc like we're getting here. You're going to get a shell. But that's a method that we're not going to cover in this class. That's section 7.3. We're going to stop at section 7.2. 7.3 is something you'll see in Calc 2. Let's find the volume of one disk. As before, the volume is going to be equal to pi r squared times the thickness. Let's just cut right to the chase. Pi r squared times dy. Now the dy is telling you that r has to be in terms of y. So this is your radius. If I put a point here with general coordinates of x and y, what are the coordinates of this point here? No. 0 and y. 0 and y. So the radius is going to be the right minus the left. It's going to be x minus 0 or just x. But x is equal to minus y squared plus 4y. All right. That works out nice. Let's plug that in for r. Negative y squared plus 4y squared dy. And then we got to square that out. So this squares out as pi times y to the fourth minus 8y cubed plus 16y squared. So that's the volume of one such disk, or one hockey puck over here. dy. Yes, thank you. dy. To find the volume of all such disks, we're going to need to integrate. So the integration is really just adding up the volume of all such possible slices, even though they're arbitrarily thin. So it's going to be pi times integral of y to the fourth minus 8y cubed plus 16y squared dy. Now think carefully for a second. Ask yourself, what should the limits of integration be? Good question. 0 to 4, 1 to 4. Yeah. So it's in terms of y, so think about where this slice can be taken from. This slice can go all the way down to here, which is y equal 1, and all the way up to here, which is y equal 4. So from 1 to 4 would be your limits of integration. Are we okay with that? Because your region stops at 1. I mean, if they wanted to shade the rest of us and we needed the volume of this entire region, then we could do that. But it goes down to 1 per the book. All right. All right, let's integrate this thing. In fact, maybe we'll take a little bit of a shortcut. I get 30.6 when I integrate this. So pi times 30.6. 30.6 as a fraction would be 153 over 5 times pi. I'm trusting that this part of it is not that big of a deal. The hard part is getting here. So how are we doing on the setup? Setup is most of the battle on these. Let's move on to problem number 12. Eventually, actually pretty soon, I'm going to want you to do some of these things. So there's 4 parts to problem number 12. The function involved there is y equals 2x squared. That's this curve here. Then you've got y equals 0 and x equal 2. So y equals 0, of course, is the x-axis. X equal 2 is this vertical line. Now this shape is going to get rotated around various axes. So in problem number A, it's rotated around the y-axis. In problem number B, it's rotated around the x-axis. Let's take a look at part B first. Take your slice perpendicular to the axis of rotation. So that's going to be another dx slice here for us. dx. We want to find the we want to find the volume of one such slice. All right, so this is y equals 2x squared. So volume of one slice. Volume is going to go pi times r squared. R again is going to be the top minus bottom. So y minus 0, of course, is going to be a radius. And that y is going to equal 2x squared. So I'll get 2x squared squared times dx for the thickness. We can clean this up. 2 squared is going to be the 4 pi x to the 4th dx. What should be our limits of integration? Good. 0 to 2 should be your limits of integration. 0 to 2 of 4 pi x to the 4th dx. So 4 pi x to the 5th over 5 between 0 and 2. 32 times 4, 128 pi over 5. let's see if we can't take a quick look at this on Desmos. Are we doing okay with problem 12b? Is that one looking all right? Helen? Doing all right?
Yeah, I was
Okay.
just thinking about A.
Okay. Yeah, A is going to be a little bit different, and we'll see that in a second. But let me change this function. So we've got 2x squared. And change our window a little bit. Let's go from, say, negative 10 to 10. So here's your shape and profile. And what we're going to do is we're going to look at one little slice. So let's put a little slice in here. Oops, not there. Yeah, I guess that does show us our slice. So there's our little slice. And we're going to rotate this around the x-axis. So as we rotate it around the x-axis, that little slice sweeps out a volume. Yay. And you can see our little disk right here. We want to find the volume of that one disk. Let's rotate this around a little bit, see if we can't get a different viewer perspective on this. I think we can make alpha a little different here. So we'll spin it around. Oh, that's the one I wanted. There. So more of a profile view. You can see our little disk. We're going to find that volume of that one disk and then add it up for all such possible disks between 0 and 2. And that's what we did. This picture is going to change, though, if we rotate things around the y-axis. Let's take a look at what happens when we rotate around the y-axis. So that's this one over here. What kind of a slice am I going to have to take when we rotate around the y-axis? Horizontal. So let's do that here. Taking a horizontal slice. Okay. Now, can you notice something different about this when we rotate around the y-axis as opposed to the previous one when we rotated around the x-axis? There's something qualitatively different. There's a gap here, right? When we rotate it around the y-axis, are we going to trace out a disk anymore? No. You're going to have a hole. You're going to effectively trace out a washer. So how are we going to find the volume of a washer? It's not that hard. And just think of it as this outer cylinder subtract off the inner cylinder, right? So you just got two different radii to deal with, but that's what we're going to do. Is we're going to start out with an outer cylinder and subtract off the radius of the inner cylinder. So let's put a point here on this curve, call it x and y, and then come up with some other points, like over here. What would the coordinates of the point on the y-axis be? 0 and y. Good. 0 and y. And this point right here, what would its coordinates be? Yeah, 2 and y. So as we rotate this around the axis, let's see, we're going to have to try and find the volume of one washer. And let me stress, you're getting a washer because this figure is not flush with its axis of rotation. If it was flush, like the previous problem, then you wouldn't have to worry about a washer. But the volume of the washer is going to be pi r2 squared, that is the outer radius. So we'll call that r2, just in time for the movie coming out, right? And then the inner radius we'll call r1. So pi r2 squared minus pi r1 squared times the thickness. That's going to be the volume of one washer. So now we got to go through and figure out, well, all right, gosh, what's what? Let's work on that. This would be which radius? R2. Good. And then this would be R1. So let's see if we can't come up with a couple expressions for R2 and R1. Now when you're working with these radii, the distance or their length is always going to be right minus left or top minus bottom, depending on if you have a dy slice or a dx slice. In this case we have a dy slice. So it's going to be right minus left. So R2 is going to be 2 minus 0. What's R1 going to be? Got to work with the more general coordinates. X minus 0. Except there's a little bit of an issue we have here. R2 is fine because that's just 2. R1, we don't have an expression, at least tailor-made, for X. So what are we going to do to get an expression for X? Go back to the function. We're going to solve for X here. So X is going to be, well, yes, square root of y over 2 would be X. So square root of y over 2 is X. Boy, there's a lot going on here, right? Let me pause here. Are we okay with where we're at so far? We got a washer as opposed to a disc because this figure isn't all butted up against the y-axis, which is our axis of rotation. So we have to deal with an outer radius and an inner radius. Here's your inner radius closest to the axis of rotation. Here's the outer radius. So we have 2 and root y over 2. And I think we're ready to set up the volume of one washer. Volume of one washer. So it's going to be pi times R2 squared minus R1 squared times dy. So I just factored out the pi up there, and now I'm going to fill in R2 and R1. Pi times 2 squared minus square root of y over 2 squared dy. So pi times 4 minus y over 2 dy. And that's looking pretty manageable, despite the fact that it was a little bit of a torturous route to get here. Last step. We need to figure out the limits of integration here. That's the volume of one washer. We need to add up the volume of all such washers. Let's factor out the pi. 4 minus y over 2 dy. But what are the limits of integration here? Yeah, they're based on y, right? So 0 to wherever this gets up to. Now, if you can't read that off of the graph, all you have to do is plug in a 2 into the function. 2 times 2 squared is 8, as several of you have said. Thank you. 0 to 8. Can we skip to the happy ending on this one? Yeah. All right. You can integrate this one, okay? You're good. All right. So it's going to be 16 pi. Okay. Any comments or thoughts on those two? Jackie?
Could you back at the same
if you let's see, mm, if you shifted the graph over,
It would be at -2 and 0 instead of 0
it'd be a different figure. It would look different. If you shifted this over and then rotated it, it would look like a volcano. Right now, it looks like a cylinder that you've scooped something out of. So it would be a different figure altogether. And you might, by some magic of geometry, be able to figure out how they're related and subtract one from another somehow to make it work. It's a great suggestion to shift it over, and then you don't have to worry about that washer. Yeah, it'd be nice. But you get a different figure if you're rotating around the same axis. Yeah, so good try. Okay, so here's the game plan. The next two are going to be up to you. Now the first one here, part C, we're rotating around the line y equals 8. And the last one, I think it's rotated around the line x equals 2. So the first thing I want you to do is decide which or both of these are going to be disk or washer. So this one's going to be rotated around the line y equals 8. And this one's going to be rotated around the line x equals 2. So rotate it like that. Talk it over with a neighbor. And I'll do the big reveal in just a minute. So first decide which one of these is disc or washer, or are they both disc, both washers, etc. Look at the figures, look at the axis of your rotation. So I invite you again to talk to your neighbor, compare notes. This is your chance to interact with something other than computer or Siri, your fellow sentient human being, walking, talking, breathing. Make a friend. Find a study partner. So with respect to the first one, our figure is right here, y equals 2x squared. If you're taking a slice perpendicular to your axis of rotation, that slice is going to have a dx thickness. But our slice isn't flush with the axis of rotation. So it's going to be a washer method when we do that one. Let's take a look at this one. In this one, again, you have to take a slice perpendicular to your axis of rotation. In that case, it's going to be a dy slice. But this time, all our slices are actually going to be flush with the axis of rotation. So what kind of method is that going to be? Disc. Yeah, it's going to be a disc. So a dy slice here. So we've got a washer and a disc method. Okay, I'd like you to work on these, both of them. You can work together. Should I pause this, or should I just break it up into two videos? Because I'm going to give you a while to work on it. Pause. All right. There we go. It'd be easier to post one video. So. Slice, then when that rotates around, there's going to be a gap between here and this rotation. That gap is what creates the washer. this for the radius. The radius is the distance to the axis of rotation, not to the x-axis. Because the radius is up here.
So the only thing wrong is R1.
R1, yeah. Then that's going to change it because then the radius is going to be negative, effectively. I mean, you're really close. You might be off by just a negative sign, I'm not sure.
Okay.
But you're really close.
Okay. Try that.
Okay. Did you convince yourself which this was a just wash? Okay, it's a wash. So you're going to need R1 and an R2. So the volume would be pi times R2 squared minus R1 squared. Right? So that's good. Yeah, that's all right. So let's see. What radius is this going to be? This distance, I'll let you write it. This distance from top to bottom. Is that going to be R1 or R2?
R2.
Yeah, that's your upper radius, right? So it's going to be top minus bottom. R2, 8 minus 0, which is that. Let's look at R1. R1 is the inner radius, right? It's this here. So again, it's top minus bottom. 8 minus 1. But because our thickness is dx, you got to write this in terms of x. How can you write this in terms of x? Yeah. And then, so then it's going to be x. But that's going to be volume 1 washing.
R1 y minus 0. So y, put y equals
Um, expression for R1 squared. R1 is our
so
distance.
that
Distance between
or y is
minus 1.
and then R2 is
It's coming out to be the same thing. Yeah, I thought, like I said, I thought it was just off by a sign. Because you put in a negative 8 squared too.
Oh yeah, and then negative a squared is just the positive.
Yeah, so if you factor out the negative, then you exactly had the opposite of what you needed. R1, this is the x-axis. Actually, this is center of x. is if you're using the x-axis as your axis of rotation, but it's not. This one, rotating around the line x equal 2, so this is a washer method, not a disk method. No, I mean a disk method, not a washer method. Sorry. So there's no R1 and R2 in this problem.
And this is what happened, then I started to break some here.
redo this video in my afternoon class. Kind of felt it might have been too long of a pause. Hey, still there, maybe. All right, find out what happens. Okay, so hats off to you if you're still with us after a long pause. We'll start with this one here. We've got coordinates at x and y on this graph. If I come all the way up here, the x coordinate's the same, but now I'm at a y height of 8. Moving down, x coordinate same, y coordinate, you're on the x-axis, so the y coordinate is 0. Let's figure out some of the radii involved. Because this doesn't touch my axis of rotation, it's going to be a washer method. I'm going to need to know R1 and R2. So R1 is going to be the inner radius. It's going to be right here. And those of you who are making mistakes on this, this is where it happened. R1 is the distance between this point and this point. And when you're taking a dx slice, then that distance is top minus bottom. So R1 is 8 minus y. But then you look and you say, oh, well, I got a dx slice. So I need to write everything in terms of x's. So replace y by 2x squared. And now you've got your inner radius. The outer radius, that's the easy part. There's your R2. Top minus bottom is simply 8 minus 0, or 8. So let's put those in for our formula for the washer. You can condense the area formula for a washer as pi times R2 squared minus R1 squared. If we then multiply by the thickness, we've got the volume of one washer. Let's put that together in a formula. Volume of one washer. So it's going to be pi times 8 squared minus 8 minus 2x squared squared again times dx. So let's be careful in squaring this out. This is going to be 64 minus what? 32x squared plus 4x to the fourth dy. If you distribute this, then we're going to see that the 64's cancel. Dx, thank you. So the 64's are going to cancel. I'll be left with pi times negative 4x to the fourth plus 32x squared dx. Okay. I suggest you clean these things up before you try and put them in the integral. That's why I kind of break this off as a separate calculation, the volume of one washer. To finish this up, we need to integrate. I'll put the pi out in front. Negative 4x to the fourth plus 32x squared. What will our limits of integration be for this one? Good, 0 to 2. Whew. So 0 to 2. Let's just cut to the happy ending on this one. So, it's going to be pi times 896 over 15. Or better yet, 896 pi over 15. Whew. All right. How's that one looking? We okay? I think the big trouble for a lot of people here was the R1, getting the top minus the bottom. I do strongly suggest that you put points on these curves so that you can calculate your radius accurately. Top minus bottom, or in the case of a dy slice, right minus left. Anything about part C before I move on to part D? Okay there? All right. Part D, we're going to rotate around the line x equal 2. That means you have to take a perpendicular slice or a dy slice. Since this slice, no matter where you take it, actually touches your axis of rotation, it's going to be a disk method. So if it's a disk method, that's great. That's easier, less work to do. Volume of one disk. Well, first, like the last one, it would help out if I had the radius. And that radial distance is going to be the right minus the left. Now, when you're subtracting, trying to find this distance in the x direction, you're going to subtract the x coordinates. So the volume is going to be pi times r squared dy, or pi times 2 minus x dy. But x doesn't really help us out because we've got a differential term of dy. We need to integrate with respect to y. If you solve our equation, y equals 2x squared for x, like we've done before, you get pi times 2 minus the square root of y over 2 dy. Oh, this needs to be squared. Okay. Last thing to do, well, you know what? Maybe while we're here, let's square this out. That's going to be 4 minus 2 square roots of y over 2 plus y over 2 dy. Let's see, do I want to clean that up a little bit more? Maybe a little bit. You're right, it'll be minus 4 there. Thank you. So minus 4 right here. Let's see. Can we apply some Photoshop? Yes, we can. Thank you. Minus 4 there. Yeah, 4. Let's see. 4 minus 4 over root 2 times y to the 1/2 plus 1/2 y dy. So if you're stuck finishing this off by hand, I got rid of the constant here. I wrote this as a power of, y to some power. That way I can use my rules for integration. Those rules for integration are going to help out when we integrate from 0 all the way up to 8. 4 minus, let's see here. No, I was trying to think of this. 2 squared divided minus 1/2. 2 to the 3/2. Y to the 1/2 plus 1/2 y dy. Are you interested in the gory details, or do you want the happy ending? Happy ending. All right. Happy ending on this one is going to be 16/3 pi. Whew. Man. Get out the oxygen bottle on these things, man. They're pretty long. Okay. A couple more here to practice. Let's flip over to the back of our handout. We've done everything, huh? Well, I guess it's time to go then, huh?
Yeah.
All right. Let me give you some homework.